right, folks, I'm going to do some solving on this worksheet here. So the first page is a little bit of an orientation to the Fibonacci numbers and the golden ratio. Most people have seen the Fibonacci numbers before, but if you haven't, you should go look on online and in various places for cool stuff with the Fibonacci numbers. But anyway, it's a sequence. It starts with the 1 and a 1, and then to go forward, you take the last two terms and add them together. So F1 is 1, F2 is 1, F3 is 1 plus 1, which is 2, F4 is 1 plus 2, which is 3, F5 is 5, F6 is 8, F7 is 13, F8 is 21, F9 is 34, and F10 is 55. And you could imagine that if you wanted a really large Fibonacci number, it'd be a pain to sit down and calculate all of these out. So our goal is to use diagonalization to find a nice-ish formula for calculating any Fibonacci number that we want. One of the things that might be surprising to find in this formula is that the golden ratio pops up. And the golden ratio is this number, 1 plus the square root of 5 over 2. Again, that's the kind of thing where if you look online, you'll see all sorts of cool stuff about the golden ratio, although come at it with a little bit of skepticism because not everything that purports to be golden is. And one way of thinking about the golden ratio is that it's the root of this polynomial lambda squared minus lambda minus 1. And there's another root of that polynomial. It's 1 minus the square root of 5 over 2. And as far as I know, it doesn't get like a consistent name. So I'm just going to call it the bronze ratio on this worksheet. And I've written this with lambdas because, as you might suspect, we're going to figure out something that might look like a characteristic polynomial for a linear transformation involving some lambdas. So let's work this stuff out. So if I want to do phi times c here, I'm going to do 1 plus the square root of 5 over 2 times 1 minus the square root of 5 over 2. And this has the effect of rationalizing. Oh no, what happened? I lost my shared screen. Resume share, please. All right, hold for a moment, folks. Here we go. Okay, we're back. This has the effect of rationalizing the numerator. So when we do this, we're going to get 1 minus 5 over 2, which gives us negative 1. Is that right? Why do I feel so? Oh, I was like, it's supposed to be negative 1. I didn't multiply my 2's in the denominator. There we go. So now we get negative 4 over 4, which is negative 1. So that means that the product is negative 1. And that means that if I think about reciprocals, the reciprocal of 1 over phi is going to be negative c. And the reciprocal 1 over c is going to be negative phi. Now let's add these jokers together and do 1 plus root 5 over 2 plus 1 minus root 5 over 2. We see that the root 5s are going to cancel. We end up getting 2 over 2, which is 1, which means that 1 minus phi is c, and 1 minus c is phi. So these are some handy things that we're going to use later on when we end up row reducing some stuff, believe it or not. Also, one of the things that I suggested you might want to do is go check out this Donald Duck and Math Magic Land video. He discovers along with you that the ratio of the whole length of one of these legs on the star to the tip to one of the intersections with another leg is the golden ratio. And I don't know, I find this one sort of trippy. You see that if you draw your star, I'm bad at drawing these regularly, you can see there's like another star embedded in here, and then there's like another star in here, and you can kind of keep going and it zooms out. It's really trippy. Anyway, enjoy that. All right, so these are just some basic facts about Fibonacci stuff and the golden ratio. Let's get to the linear algebra. Okay, here we go. We've got a linear transformation It's given by this matrix multiplication. It takes the two entries in our vector, adds them together. That's our new first entry. And the second entry in our vector, it just moves the first entry down to the second entry. We did this in class. We sort of looked at what happens when we repeatedly apply our linear transformation, but let's go through it one more time. If I do L of 1, 1, my linear transformation tells me this is going to be 2, 1. And notice that that's L of F1, F2, giving me F3, F2. So it gives me F1 plus F2 and F2. What did I do? That I put these in wrong. Let me put them in this way. I'll move the 2, 1 up there. There we go. That looks better. So this gives us F3, F2. So that's the first step. And if you go on to take more math classes, you'll see that there's a proof of this by mathematical induction. But the idea is if we believe that this happens, then like L to the n minus 1 of the vector 1, 1 should give us Fn plus 1 and Fn. And then if we plug that into L again, so if I do L to the n of 1, 1, that's going to be L of Fn plus 1, Fn, shoop, shoop. And my linear transformation says, all right, take those, add them together. So I get Fn plus 1 plus Fn, and then Fn plus 1. And of course, that top entry is the formula for the n plus second Fibonacci number. So get Fn plus 2, Fn plus 1. So this is sort of a ... proof, and that type of proof has a formal name. It's mathematical induction, but we'll see that later. Okay, so let's do the eigenstuff here. Let's find the eigenvalues of the matrix A. And we know that the way that we find eigenvalues is we calculate the characteristic polynomial. So it's going to be the determinant of A minus lambda I2, which means we're calculating the determinant of this matrix A, and we subtract lambdas from the diagonal. 1 and negative lambda. What we get when we do this is 1 minus lambda times negative lambda minus 1, which comes out to be lambda squared minus lambda minus 1. And if we look back at that previous page, that was where the Fibonacci, the golden ratio and the bronze ratio came from. They were the roots of this polynomial. So this is lambda minus phi, lambda minus c, and that tells us that our eigenvalues are phi and c. Oops, of course, draw lambda instead of c. There we go. All right, so now if we want to find a basis for the eigenspace, this is where that row reduction comes in. So let's see how this looks. Let's do lambda equals phi first. So when we're doing this, we need the null space, or the kernel, of A minus phi I2, which means we're looking at this matrix, 1 minus phi, 1, 1, and phi. And we want to row reduce this thing to get down to the null space. In fact, I'm going to want to row reduce this, so let me move this over here. There we go. So the first thing that I want to do is I want to notice that 1 minus phi, we worked that out earlier. We worked out that that was c. So we have c, 1, 1, phi. And what I'm going to do is I'm going to take 1 over phi, row 1 to row 1. I want to get a leading 1 there. And when I do that, now remember that 1 over phi, we worked out that was 1 over c is negative phi and vice versa. So we're going to get a 1. And we get this 1 over phi, 1 over c, and then we get a 1 and a phi. And that is no row reduction here. This is just legitimately equal to 1 and, oh, that was a negative phi down there, right? Because it was negative lambda. Okay, fixing that. Now we get 1 negative phi, 1 negative phi. And we're going to row reduce this by taking row 2 minus row 1 to row 2, and we get 1 negative phi, 0, 0. And now if we think about this as telling us that x is x plus negative phi y equals 0, because we sort of got this implicit, right? We're multiplying by xy. We're setting it equal to 0. This tells us x minus phi y equals 0, which tells us that if y is any real number, then x is going to be phi times that real number. So a basis for the eigenspace, E phi, is composed of the single eigenvector phi and 1. And when we do this with lambda equals c instead of phi, then what happens? Well, let's see. So, let's see. Get it? Sorry. 1 minus c, 1 minus c. That is going to be equal to phi 1 minus c. As you might expect, we're going to do 1 over phi times row 1 to row 1. And we get 1 over phi, 1 negative c. We know that 1 over phi is negative c. So this is now equal to 1 negative c. And when we row reduce this thing, same moves as before, row 2 minus row 1 to row 2, we're going to get 1 negative c, 0, 0. And the same moves tell us that the basis for the eigenspace EC is the single eigenvector C1. All right, so that gives us our eigenspaces and the sort of principal eigenvectors that we're going to take to be a basis for those. And so now we're going to go through the motion and diagonalize. So here's what we're going to do. We're going to make the eigenbasis. So our eigenbasis T is the set phi1, C1. Notice that these are indeed linearly independent vectors, right? Phi is not phi1 as a vector is not an integer multiple of C1 as a vector, right? If I wanted to get from phi to C, I'd have to multiply by like whatever, negative C times C or something like that, but then 1 times that is not 1. So these are two linearly independent vectors in R2, which makes them a basis for R2 by one of our dimension theorems, which means it is true that we can diagonalize L. So why is this true? It's because T is a basis, well, I guess, for R2. And so as long as our eigenspaces, if we take their bases together, we get a basis for our ambient space, in this case R2, then we can diagonalize our linear transformation. And so now if we want to write down the diagonal matrix that represents L with respect to T, well, we just match up our eigenvectors, our eigenvalues with the order of our eigenvectors. And so that's our diagonal matrix D that represents L with respect to T. I put phi first because phi1 is the first eigenvector in T, well, I guess first vector in T, and then C second because C1 is the second vector in T. And we want to make sure that our eigenvalues get paired up with their associated eigenvectors. So these should match and these should match, and they do. I think I've changed this worksheet since I gave it to you because I realized there's a quicker way to get the inverse of one of these matrices. So if we calculate P from T to S, remember what we need to do is we need to take our T basis and give it coordinates in the S basis. And since S is the standard basis, there's nothing to do here. Our vectors already come in the right form. So I guess I'll color code them as I put them in here. And in order to find the inverse of this thing, so we know that changing the basis back is essentially just undoing what we did. It should be like multiplying by the identity matrix in the first place. So what this is going to be is the inverse of this guy. And since it's a 2 by 2 matrix, what we're going to get is it's 1 over the determinant of P from T to S. So we'll have to figure that out, but I think it's not going to be too bad. Times this thing where we scramble things a little bit. So I believe we are going to switch the green one and the golden ratio. And we leave C alone, but we give it a negative sign. And we leave 1 alone, but we give that a negative sign. So I think that is the matrix that we should get. I feel pretty good about that. Yeah, we switch A and D, and then we change the signs of B and C. And that's actually, we talked about cofactors back in the day. This is the cofactor matrix of P from S to T to S. And so all we need to work out here is the determinant of P from P S from T. So let's get the determinant of this guy. S from T is going to be phi minus C. And oh gosh, I guess that's one I should have put earlier to work out, but that's not going to be too bad. We get 1 plus root 5 minus 1 plus root 5 because we're changing the sign of C. All of this is over 2. And so we get 2 square root of 5 over 2, which is just root 5. And so this tells us that the inverse matrix here, the one that goes from S to T, is going to be 1 over root 5, that scalar, times this matrix 1, negative C, negative 1, phi. All right, we're almost to the point of magic happening here. Oh no, it looks like I've lost. Shoot, I have a typo. I tried to go fix a typo here, so ignore that line. Bad Gibbons. I'll fix that in the actual worksheet. We want to turn this into this diagonal process. So we want to end up in the standard basis. We want S from T. And then we do D n minus 2 times. And then we, in order to start in the standard basis, we have to go from to T from S, and we're going to multiply by 1, 1. So that is the formula that we want there. So, oh boy. Okay, let's work this guy out. So let's do our scratch work down below. All right, P T to S, we said that was the nice one. That was the one where we just put in our eigenvectors. And then D to the n minus 2. Well, it's diagonal, so that's super awesome. That's just going to be phi to the n minus 2. And then C to the n minus 2. And then we had P S to T. That we had a scalar of 1 root 5. So I'm going to move that to the front. And what we did was we made the little cofactor matrix here. So we swapped the 1 and the phi, and we changed the sign on C and negative 1. Then we're going to multiply this by 1, 1. Oof, okay. So it's kind of a lot, but that's all right. We'll get through it. So let's multiply 1, 1 by the first matrix. So then we're going to get 1 over root 5 times phi1, C1. I guess actually, since matrix multiplication is associative, let me put some parentheses on here and let's work these out in tandem. So let's see, if we do the first set of parentheses, we're going to get, oh, that works out quite nicely. We get phi times phi to the n minus 2 and then C times 0. So we get phi to the n minus 1 for our first entry. When we get to the second entry, we're going to get a C to the n minus 1 because I have phi times 0 and then C times C to the n minus 2. And then I've got a 1, 1, which tells me I'm going to get a 1. I'm going to get phi to the n minus 2 and then C to the n minus 2. Minus 2. So that took care of my first parentheses, set of golden parentheses. And let's do the next one. So I'm going to get a 2 by 1 vector here. I have 1 minus c for my first entry and -1 plus phi for my second entry. And we can simplify this vector. So let's rewrite this thing. This is going to be equal to 1 over root 5 phi to the n minus 1, c to the n minus 1, phi to the n minus 2, c to the n minus 2, times, well, 1 minus phi is the golden ratio. 1 minus c is phi, and -1 plus phi is going to be negative c. And now we can multiply this all out, and we are almost there. So let's see, we're going to do phi to the n minus 1 times c to the times phi. So we're going to get phi to the n. And then we're going to get a c to the n minus 1 times negative c. So we're going to get minus c to the n. And in the second coordinate, we're going to get the same thing, but with different powers, n minus 1, c to the n minus 1. That's actually a nice reality check because, you know, if we're getting a formula for n, we should just expect that we're going to end up with this kind of nice n in the first coordinate, n minus 1 in the second coordinate. So this tells us that our formula for the nth Fibonacci number is going to be 1 over root 5 times phi to the n minus c to the n. And that's pretty awesome, right? Because now we've got this closed formula. So your next task is to take your formula, simplify it as much as you would like to. I don't know, let's see, what does this look like? This is 1 over root 5 times 1 plus root 5 to the n. That's not going to simplify, over 2 to the n minus 1 minus root 5 to the n over 2 to the n. Numerator is not going to simplify too much, but we can at least pull the 2n out if we like to. So you can do 1 over 2 to the n root 5 times 1 plus root 5 to the n minus 1 minus root 5 to the n. And just take a moment here to kind of marvel that when we do this, we're going to get an integer at the end of the day. So I asked you to take your birthday, write it down in month-day format, just sort of smush them together. And that tells me that, so my birthday, April 13th, I dare not add the year because then you'll know how old I am, but also it might not be able to calculate this on Wolfram Alpha, but F413. So the 413th Fibonacci number is going to be 1 over 2 to the 413 times root 5. Yikes. 1 plus root 5 to the 413 minus 1 minus root 5, all of that to the 413. And let's work this out. I think I can remember this formula, so let me switch here. Let's see, do I have, let's go home, let's pull up Wolfram Alpha. Let's see what we get. You can see I was doing some matrix stuff to make sure that some things on our last exam row reduced nicely. All right, so we're going to do 1 over 2 to the 413 times root 5, square root of 5. And that is the end of our parentheses, times. Okay, 1 plus the square root of 5 to the 413 minus 1 minus root 5 to the 413. Any guesses on how big this is going to be? That's kind of a fun one to think about. So if you want, pause the video and see if you can think about how big this is going to end up being. And that should be all our parentheses look matched up. Let's see what we get. Holy moly, look at that result. That is approximately, let's see, 10 to the 5 is 100,000. So we have like 900,000 times the number of atoms in the visible universe. So that's a pretty big number. That's the 413th Fibonacci number. It is 9.2 times 10 to the 85th. That's a pretty honkin' big number. Imagine sitting down and trying to calculate that out. Let me Can I copy this bad boy? I copy all of that. Come on, let me copy it. There we go. Copy. Yikes. That's wild. That's a really, really, really big number. I mean, I knew it was going to be big. I guess I sort of forgot that I was going to have that many zeros at the end, but let's pop in here. F413 is equal to text box. Can I paste it? Yeah. Yep. Let's make the font a little smaller so we can maybe fit it on one line. Minus. There we go. Yeah, so that's the 413th Fibonacci number. Pretty big. If you like to think about this sort of thing, I've asked you, how long do you think it would take to calculate the nth Fibonacci number, in my case, 413th Fibonacci number, by adding up all the previous numbers? I don't know. I think my brain craps out at about, like 10 to the 70 when I need to do addition here, but it's sort of a fun little counting question. I don't think that would take me 10 seconds to add up numbers of that magnitude, but if you want to make assumptions like that, that would be kind of fun. So this turns out to have 86 digits, I guess. Holy moly. And anyway, that is the worksheet in a nutshell. So we use Wolfram Alpha here. Got to give credit when we use our little tools. If you find this kind of fun, it would not be that hard to write a little function in Python or whatever your favorite programming language is, where you could just plug in n and spit out the nth Fibonacci number. And you can amaze and delight your friends. I hope you found this kind of exciting. I know I did. And I will see you in class soon.